Hello everyone. I am Sayoni. I'm a research scholar from IIT Kharagpur, and I will be taking this tutorial session for the course of Foundations of Cryptography. And this will be the regular timing every Saturday from 6 p.m. to 8 p.m. And this Zoom meeting link actually, I think it works for 40 minutes and then it automatically gets paused or stopped. So whenever this meeting link gets stopped by default, you can join again in the same link. So I will be I'll be starting the meeting for the same link. So you please join back in the same link. Okay. And
Okay, no problem.
yeah. So, and if you have any question, you can unmute yourself in the middle time. Whenever so I will be basically sharing my screen. Okay. Someone is saying audio is not audible. Is it the problem for others also? Otherwise, I will request Gayatri to join. Just leave and join back.
Yes, you are audible.
Okay. Okay. Then I will ask Gayatri to join again. Sure. So, okay, I will be presenting my screen and I will actually try to use whiteboard. So I am not particularly sure how that will work. So I will try using whiteboard in the midtime to explain some things, and otherwise I will be presenting my PPT screen. Okay. So, so let me share my screen first. I hope my screen is visible, right?
Yes, ma'am.
Okay, thank you. So let's start. So basically, as you know, this will be a 12-week course. So I will be taking a tutorial session for 12 weeks, and I think there will be a final session for 1 hour uh, at the end. So that will be, maybe it will make it 13-week tutorial session. Okay. So let's proceed. Uh, So for the first week, as the main course schedule goes on, so first week topics are these: historical ciphers and cryptanalysis, perfect secrecy, modern cryptography, and pseudo-random generator. So basically, each week you will have also some assignment, right? So you will try to solve those assignment on NPTEL website, and then so I every week I will be discussing that particular week's topics, and in the next week, once the assignment submission date is over, then I will discuss the previous week's assignment questions also. So for this week, I will not discuss any current courses assignment question because the submission date is not yet over. From next week onwards, we will discuss first the previous week's assignment questions, and then we will discuss the current topics, some questions from current topics. Okay. So that's enough for introduction. And so let's start. So first problem that we discuss, you can read from my screen. So consider an instance of shift cipher with the probability distribution over the message space as follows. Probability of message being A is 0.4, probability of message being B is 0.3, and probability of message being C is 0.3. So what is the probability that the ciphertext is D? So since this is an introduction section, so I think so let me just first discuss what is shift cipher. So as you can understand from this question, that the plain text space or message space just consists of 3 letters from the alphabet, that is A, B, and C. And the way shift cipher works, if you remember from the lectures, so it is there must be some particular key whose value remains between 0 to 25, So there are 26 letters in the English alphabet, right? So from A to Z, we start numbering them from index 0. So A being 0, B being 1, C being 2, and so on. So in that case, let's say how does shift cipher work? So let's say shift cipher key value is 2. Okay. Then if your plain text is given as E and your key is 2, then E will map to E plus 2, that is 2 letters shifted from the plain text message E, that is E, F, and G. So G will be your cipher text. Like that, shift cipher works. So for English alphabet text being the plain text, for each particular value of key, one message gets mapped to ciphertext corresponding to that much number of alphabets later. Okay, hope I am clear. So for this question, it is asking that what is the probability that the ciphertext is D, right? So anyone would like to answer? You can unmute yourself and answer if you want. Also, you can make use of chat. 3/26, someone, Gayatri is saying. Okay. Can you explain? You can unmute yourself and explain why do you think it is 3/26? Okay. So see, our final objective is to 0 means A likewise. The key of the shift cipher is not specified in the question. Okay, so ciphertext will be D in how many cases? Your plain text consists of just A, B, and C. Okay, so A will map to a ciphertext D if your key is 3. Yes, Karan Kishore, your answer is right actually. So let me explain. So if your plain text is A, then if your shift cipher key is 3, then only A will map to D, right? So A will be shifted by 3 letters. So B, C, D. That will be one case, and that will happen with how much probability? That probability is point. Let's just go to the answer. So here there can be 3 things. That message is A and key is D. D means 3 starting from 0, right? Then your ciphertext becomes D. Otherwise, if plain text is B, then if key is 2 or C, then B gets shifted by 2 letters and the final ciphertext is D. That is another case. And if plain text is C and your key is 1, then C will map to D, and that is this case. So there are 3 disjoint cases, right? And for each of them, if we put the probability, so this is given probability of M equal to A as 0.4 and probability of key being D. So as there are 26 key available, so each key gets selected with equal probability. So it's 1/26. And that's how we get this final output as 1/26. So this is the answer. Okay. So thank you, Karan Kishore, you gave the right answer. So let's proceed to the next question. If you have any doubt, you can stop me in the meantime and ask. Okay. So okay, this is the next question. Consider an instance of shift cipher with the probability distribution over the message space as follows. Probability of M being A is 0.3. Probability of M, that is the plain text, being B is 0.6, and probability of plain text being C is 0.1. So again, you can see the plain text space just consists of only 3 letters, A, B, and C. Why I am saying so? Because if you see the sum of this probability, 0.3 plus 0.6 plus 0.1, this is 1. So in this question, no other plain text alphabet is possible basically. All three are covering up the whole probability. Okay, so plain text just consists of A, B, C with different probabilities. And then it is saying then identify the correct statements from the following. So multiple option could be correct in this question. Okay, there is one. So option one is saying probability that the ciphertext is D is the same as probability that the ciphertext is E. So yes, your answer is correct. I think this is Bhavya Parikh has answered. So yes, this is the correct answer. Thank you. So I think this is very much similar to the previous question as I explained that the ciphertext being D, that probability can be calculated in the just analogous manner as the previous question. And ciphertext being E is also calculated in the same way. So there is three disjoint cases. Ciphertext being D is possible if plaintext is A and the key is 3, or plaintext is B and key is 2, and plaintext is C or key is 1. So all of them will be occurring with probability 1/26, and same goes for ciphertext E. In that case, probability of message being A and key being 4, key being 5 will be considered. 0, 1, 2, 3, 4, 4. So starting from 0, if key is 4 and message is A, so A will be shifted by 4 letters and be giving E, and so on. Okay. So I think this should be clear to everyone. Okay. So let's proceed to the next question. So this is a question on perfect secrecy. Which of the following conditions is or are sufficient to get a perfectly secure encryption scheme? So options are given as ensure that key generation algorithm outputs a uniform random key from the key space. Ensure that the encryption algorithm is randomized. Ensure that the key is as large as the plaintext, or none of these. Two, Bhavya Parikh is saying, ensure that encryption algorithm is randomized. Okay, we will see the answer 1 and 3, Karan Kishore. Well, so the answer is actually completely varying. Someone has said 2, someone has said 1 and 3, someone has, Nagaveni has said 3. Anvesai Singh 1 and 3. Okay, so basically the answer is actually none of these. Okay. Okay, Harini is saying 4. Yes, none of these is the correct answer actually. So let me just recapitulate what perfect secrecy is. So in perfect secrecy, you say that in an encryption scheme, we call it perfectly secure if the adversary has perfectly no advantage apart from randomly guessing the right key. Okay, so let's say we have, so as you know, one-time pad is an example of perfectly secure scheme. So what happens in one-time pad is that your message space, your key space, and your ciphertext space all have the same size. Okay, if we consider, let's say, n-bit string as possible message space, so the size of ciphertext, size of plain text, and size of key, all of them are of n bits. Okay, then you can you are using a particular key for a particular message only once, right? So that is why it is called one-time pad. So a particular key is never repeated. Okay, you just randomly select one key from the key space and you use it to encrypt a given message. Okay, now the condition, so the question was which of the conditions are sufficient. So the first option, key generation algorithm outputs a uniformly random key from the key space. This is a necessary condition, of course, for a scheme being perfectly secure, but that condition is not sufficient. So with that, another condition is required, which says that all the message space, key space, and ciphertext space have to have the same size. Okay, and the keys should be uniformly randomly chosen from the key space. So if these two conditions satisfies, then according to Shannon's theorem, the scheme will be called perfectly secret. Okay, so this condition is not sufficient. This is a necessary condition, condition 1. And encryption algorithm randomize that is not necessary for perfect secrecy, because in perfectly secret scheme you usually like if we take the one time pad scheme, then you use one particular key only once. Okay, you don't use that key twice. So randomization of encryption algorithm is required, because even if you use the same key for the same message again, due to the randomization your ciphertext will be different. Okay, that condition is required, that we will see for actually practically implementing some scheme. But perfect secrecy is something which is not practically achievable or practically deployable, because in perfect secrecy we need the key space to be exactly equal to the message space, which is not really the practical scenario. So in real world you may have several gigabytes of message which you need to encrypt. So you can't have several gigabytes of key to encrypt that message. Of course, you need some shorter key, and you want to reuse that key again and again. So you have seen these things for limitation of perfect secrecy, right? So those are limitations of perfect secrecy. Perfect secrecy is something perfect. And as we know, in real world, nothing perfect works actually. So we need to compromise in certain level. So anyway, so in perfect secrecy, the adversary can can be allowed to use uh, cannot be allowed to have any extra advantage rather than randomly guessing the key. Okay. So and the third option says key is as large as the plain text. Uh, so this is also a necessary condition, but not sufficient, as I said. So the correct option of this question is none of these. So proceeding to the next question. Barnum cipher. Okay, so what do you mean by that? I mean, you were answering to something. Okay, anyway, let me proceed. Uh, so I think this is a very easy question. Okay. Problem 4. So this is, I think everyone can answer. So I will just wait for your answer in the chat. Which is the valid condition for perfectly secure encryption scheme? Correct. Okay. So Virup Sarkar, Anisha, Harini, Bhavya, Aryan, Karan Kishore. Okay. You are very much correct. So, what we need to ensure in perfect secrecy is that whatever prior information we have about the message space before we see any ciphertext, only that much information is available to some adversary once he or she has seen the ciphertext. Nothing extra. Absolutely nothing extra should be determined by seeing the ciphertext about the underlying plain text message distribution. So that is what we are saying, that once you have known the given ciphertext is small c, what you can infer about the underlying message small m is nothing beyond what you would have already known, that what is the probability of the plain text being small m in the a priori. So okay, that is the very much basic condition for perfect secrecy. So next question. So this is some problem to solve. This is an interesting question. Let us assume a symmetric key encryption scheme with message space m equal to 0 to 13. Okay. So all numbers 0 to 13, they belongs to the message space, and key space is given as 0 to 14. Key generation algorithm chooses a uniform key from the key space. Encryption and decryption are defined as follows. So encryption of message M with key K occurs as M plus K mod 14, and decryption occurs for ciphertext C with key K as C minus K mod 14. So is this scheme perfectly secure? That is the question. I will wait for your answer. You can take let's say 1 minute of time and think and get back. If you have paper and pen, you can just uh, have some rough calculation. You can use the same condition that we just discussed, probability of plain text being small m provided the ciphertext being C should be exactly equal to the probability of message being A, that is known to adversary a priori about the message distribution. So whether that condition is satisfied or not in this case. Note that message space size is not same as key space size here. So K 0 to 100, what do you mean, Bhavya? K key space is given as 0 to 14, right? That is the given key space. You have to say whether this given scheme is perfectly secure or not. No, K is not 0 to 25. Okay, Ovirup Sarkar is answering that it's no, because I think you meant to say plain text length equal to ciphertext length. So here they are not specifying about the bit length actually. They are all integers. Messages are integers in the range 0 to 13. Keys are integers in the range 0 to 14. And ciphertext you can calculate in this way, how much they go. So it's all mod 14, right? Ciphertext, because you take mod 14 of the output. So ciphertext space is also 0 to 13. So message space is 0 to 13. Ciphertext is 0 to 13. Key space is 0 to 14. Okay. So, okay. I think I should discuss the answer. And as I said before, if this meeting ends, you can just join in the same link again. Okay. Not perfectly secure. Karan Kishore is saying, say M is 1. Correct. You are actually on the correct direction, Karan Kishore. So yes, your answer is correct. This scheme is not indeed perfectly secure. So I can just discuss the answer. So you can see in my screen that each message occurring of a plain text is 1 by 14, right? Because the plain text space size is 14. So message can be 0 to 13, that is the complete message space has size 14, and each message, plain text being 0, plain text being 1, all of these has equal probability of being 1 by 14. Okay. Now, if you check what is the probability of message being 0 given the ciphertext is 0. So that can occur actually in two cases. Okay. One is message is 0 and key is 0. Then your ciphertext becomes 0. And another case is message is 0 and your key is 14. Then also 0 plus 14 mod 14 makes it 0. So ciphertext will be 0 provided uh, message was 0 will occur in two cases. Two possible values of key is possible. So because key space is of length of size 15, so key can be 0 to 14. So key space size is 15, and each key can be chosen uniformly randomly over the key space that is occurring with probability 1 by 15. And in two possible values of key, we can see that message 0 maps to ciphertext 0. So that makes this probability 2 by 15, which is clearly not equal to 1 by 14, right? So we can say, or we can see that probability of message being 0 when ciphertext is 0 is not equal to probability of message being 0, which is necessary condition for perfect secrecy. So clearly this condition is not satisfied. Hence, we see that the given encryption scheme is not perfectly secure. Hope I am clear. Okay. So if you have any doubt, you can stop me and ask. Okay. So let me proceed. So let us recall encryption with one-time pad. If the key is k equal to 0 to the power l, that is l length bit string of all 0, we get encryption defined as m XORed with key k. Okay. And the ciphertext is the plain text itself. Clearly, if key is all 0, then your message being XORed with a all 0 string will map it to m itself. So ciphertext is the plain text itself, right? So one considers to modify the one-time pad by only encrypting with k not equal to all 0 string. Is this modified scheme still perfectly secret? Explain. So one has, you know already about the one-time pad. So this is how one-time pad encryption is defined, right? So your message is a L-bit string, your key is a L-bit string. You XOR them and you get your ciphertext. And one particular condition occurs when your key is 0, chosen to be all 0, right? Then your message is the ciphertext, right? Or in other words, your ciphertext itself is the message. So someone may think that, well, seeing the ciphertext, I exactly know what the plain text is. So I don't want that to occur. So that's why I modified the one-time pad encryption scheme. And for that, what I do is that I don't allow the key to be all 0. So I only sample key from the space of size actually 2 to the power l minus 1. So number of strings, number of L length strings is 2 to the power L, right? Binary string. So each L bit can be 0 or 1. So this possible number of L bits binary strings are 2 to the power L. And one is considering to exclude this particular string 0 to the power L. So he is left with key space of size 2 to the power L minus 1. Okay. Now, if this happens with one-time pad scheme, is the scheme still remaining perfectly secret? What do you think? Message length not equal to key length. This is necessary condition for perfect secrecy. So, absolutely correct, Karan. So, yes, that is the answer actually. So, if you exclude one particular key, okay, then your key space length becomes lesser than your message space length, which is not good to achieve perfect secrecy. So this scheme does not remain anymore perfectly secure. Also, from like just to mention from the intuitive perspective is that one who was thinking that I will exclude this particular key k of all 0, the problem is that the adversary does not know that the key was chosen to be all 0, right? Although you are thinking that key is all 0, so ciphertext is exactly equal to the plain text. So ciphertext itself is revealing the plain text, but that's not a problem because the adversary does not know what the key was chosen to be. Key was chosen to uniformly randomly over the all L-bit string space. So there can be one particular scenario where all 0 string was chosen, or there can be any other string chosen uniformly randomly from that space, right? So the adversary does not know what the key is chosen to be, and that is the whole point of secrecy, right? If you exclude one particular string, then your sample space of the key gets reduced and it is lesser than the plain text space size, and it does not remain anymore perfectly secure. Okay. This is a bias. There is a bias induced. Yes, you can say so. Okay. Okay, so let's proceed to the next question. So again, there is Gayatri has raised hand. You want to say something? You can unmute yourself. Okay, maybe it caused accidentally. Okay. Anyway, Bhavya has raised hand. You want to say something? Anyway, so you can see the question on the screen. So again, there is a plain text consisting of A and B. Key space, there are 5 keys specified and there are 5 ciphertext specified, and the mapping from plain text to ciphertext is given in this table. So basically, plain text A, upon selection of key K1 maps to ciphertext 1. Like that, the table is given for all possible combination of plain text and key, which ciphertext it gets mapped to. Now the question is, choose two positive real numbers alpha and beta such that alpha plus beta is equal to 1 and define probability of each key K1, K2, K3 to be alpha by 3 and probability of key being K4 or K5 or beta by 2. Prove that this crypto system achieves perfect secrecy. So you basically have to prove that condition gets satisfied, that probability of capital M equal to small m is equal to probability of capital M being small m provided capital C being small c, the very basic condition of perfect secrecy. So you just have to verify this. Although this is a descriptive question, I will just give you 2 minutes to also, I think this Zoom meeting is going to end within 1 minute. So you can join back in the same link. Okay, I will join in the same link. So you can just take 2 minutes and try solving. Then I will discuss. Okay. So okay, Shreyas is asking, will the recording of this meet be shared? Yes, there will be YouTube link of this recording, but I would suggest to join the tutorial session every week. What happens is that uh, once the YouTube links gets updated, so people stop joining the session actually. So I I would suggest that please join this tutorial session. It's Saturday from 6 to 8. Because if the interaction happens, then for me also I am happy to discuss and answer your questions. Otherwise, anyway, I will take the session and you will get, of course, the YouTube link later. Okay, okay, sure. Okay. So the question we are discussing now is this question on perfect secrecy. There is this table given of plain text and from plain text to ciphertext mapping in presence of keys. So we just had to check if this crypto system achieves perfect secrecy. So I think I should just discuss the answer here. How to demonstrate that this is indeed perfectly secure. So as it is given, there are two plain text, right? A and B, and each occurs with equal probability, that is half. Now we have to check each of the possible combination, that is probability of being message being A when the ciphertext C is 1, probability of message being B when the ciphertext is 1, also probability of message being A when the ciphertext is 2, probability of message being B when the ciphertext is 2, and so on. Okay. So we will just check two cases here, and all the other cases can be checked exact same way. So so let's first see that what is the probability of ciphertext being 1. So if you look at the table, so there can be two cases, right? Message is A, and in presence of message A, what is the probability of ciphertext being 1? That is that means your plaintext A maps to ciphertext 1 when the key is K1. That occurs with probability alpha by 3. So we put half into alpha by 3 here. Okay. And another case is message is B and then your ciphertext is 1. So if message is B, ciphertext become 1 when your key is K3. Okay. So that probability is again alpha by 3, because probability of key being K3 is given as alpha by 3. So you sum them up and you get alpha by 3. Okay. Now coming to here, probability of message being A when ciphertext is 1, you can write it as probability of message being A, and this is Bayes theorem, right? So in this side, you write probability of message is equal to A upon ciphertext being 1 is same as in the above part of the fraction, you write probability of M equal to A into probability of C being 1 upon M by A, and in the denominator, you write probability of C is equal to 1. This is simply Bayes theorem. It's very much basic probability thing, and you get this result as half, putting all these values here. Okay, because you calculated ciphertext equal to 1 as alpha by 3, and your probability of message being A is half, and probability of message being A and ciphertext being 1, that is key equal to K1, which is alpha by 3. So you get half. Basically, this half is equal to the probability of message equal to A, which is half. So you can see that this value is equal. But this is not enough to check just for this case. You have to check all the possible cases of message equal to A and message equal to A when ciphertext is 1, when ciphertext is 2, and so on. And if you see all these conditions are satisfied, then you say this scheme is perfectly secure. So if you calculate, you will get to see all these values, and we conclude that the scheme is perfectly secure. No audio, Akash Mittal. Yes, Akash Mittal, so you please, you can join back, I think. Leave the meeting and join back. Okay. So I am just proceeding to the next question. Which of the following is or are correct? All of keychain encryption decryption algorithm are kept secret in the crypto system. All of these algorithms are made public in the crypto system. Both encryption and decryption key are public in a public key crypto system, or only encryption key is private in a private key crypto system. So you can write your answer on the chat. This is again a very basic question, nothing to calculate much. 3 and 4, Harini is saying. Uh, well, you are partially correct. B and D, Vikas is saying. B and D, yes, you are correct actually. Karan Kishore, 2 and 4, yes. I mean, so, okay. Many people have answered right actually. So, second and fourth option are correct. So, because if you remember that for any crypto system, it is very necessary to make all the algorithms public. No algorithm are secret. Because if you implement a crypto system in a secret manner, that is, all the algorithms are secret, no one knows how do you encrypt, then it is very risky to use. Also, if the crypto system is broken, then you have to redesign a new algorithm, which is not a very trivial or easy task, right? So we don't desire this scenario actually. So all the algorithms are public, and then only if one crypto system is made public for a long time and everyone has tried breaking the system and not able to do that, then it actually gets valued, right? So we don't want the algorithms to be kept secret. Algorithms are public and verified to be secure. There are mathematical proof to prove there are mathematical proof to prove the crypto system is secure. Also, the practical attacks are also done on the systems on where the schemes are deployed and checked that this is indeed secure for a long time. And so it is not at all recommended to use your own encryption algorithm, which may seem to be very strong for on your end, but it is not actually recommended. You should use always verified public algorithms. But what is secret in an encryption scheme is the key. So key is some short uh, bit of string or whatever, and you can change the key once your key is leaked. So you just have to change your key, not the algorithm. Okay. So all the keys and encryption decryption algorithm are public, but someone had answered 3 here, but that is not correct, because in a public key crypto system, your encryption key is public, but decryption key is private to the owner of the key. So if you remember, in a public key crypto system, what happens is that, as they say in the traditional way, there is Alice and there is Bob. So let's say Alice has generated 2 keys, public key and secret key. Public key he has made public to everyone as well as Bob. So Bob knows Alice's private key. If Bob wants to send some message to Alice, then Bob uses Alice's public key to encrypt his message and send it to Alice. And because Alice only knows the corresponding private key of its own public key, she is able to decrypt the message and read it. No one else, without the access to the Alice's private key, will never be able to read that message. Okay. So in public key crypto system, the encryption key is the public key and the decryption key is the secret key. Okay. But in a private key crypto system, only one key is used. We also call it symmetric key crypto system. On the other hand, public key crypto system is also called asymmetric key crypto system, right? Because there are 2 different keys used. But in private key crypto system, in both encryption and decryption end, same key is used. So that key has to be remain private. That means only the sender and receiver knows the key. No one else in the midway has access to the key. Then only the system remains secure. Once you get to know the key, it gets leaked in some way, then your crypto system is vulnerable, right? So yes, correct answers are option 2 and option 4. Okay, so let's proceed to the next question. Let us consider an encryption scheme designed to encrypt L+1 bit messages. Well, so message space is L+1 bit strings. A L+1 bit key K is generated by first choosing a uniform random L bit string and then taking the last L+1th bit as the XOR of previous L bits. So this is your key generation algorithm being described. So your key generation algorithm does first it chooses a random key, random L bit key, and then it XOR them up, and or we can see the parity bit of the first L bits is the L+1th bit. That is how your L+1 bit key is generated. First L bit is uniformly random and last bit is XOR of all the L bits. Okay, that is how your key generation works. Now encryption and decryption are performed in similar manner as of one-time pad. So in one-time pad, we write that encryption of a L+1 bit message is XORing the L+1 bit key with that L+1 bit message. Right? Simple XOR. M XOR K is C. Okay. So that is how encryption occurs, and similarly C XOR K gives M. That is reverting back to the plain text during decryption algorithm. Is this scheme perfectly indistinguishable to an adversary? So perfect indistinguishability and perfect secrecy is equivalent idea. In the perfect indistinguishability, we say there is a game going on between a challenger and an adversary. Okay, there is Vikas is saying yes, this is perfectly secure. Okay, I will wait for more answers. What do others think? Is this scheme perfectly indistinguishable? Any more answers? Okay, no more answers. No, it is a question mark. If you are saying no, you can just unmute yourself and share. Why do you think? It is okay if you are wrong, but you can explain why do you think no. Okay, let me say that the scheme is not perfectly secure. Now you can try to think of what is the explanation. I am giving you the answer that some keys cannot be considered. Yes, intuitively you can say so, because it is clearly so as in one-time pad, which is perfectly secure, you sample the whole key uniformly randomly from the key space. But here all the L+1 bit are not uniformly random. Only L bit are uniformly random. Last key is XOR of the other key. But can you think of an attack? So in perfect indistinguishability, what happens is that there is a game going on between a challenger and an adversary. So in cryptography, we always think of security of a system in terms of some game, right? There is an entity called challenger and there is an entity called adversary. A game is happening between the two. What adversary is doing, adversary will choose two messages, M0 and M1, of its own choice and give it to the challenger. Challenger will toss a coin, fair coin, to decide which message to encrypt between M0 and M1. So it will choose one among them. Let's say bit B is chosen. So message MB will be encrypted. So B can take value between 0 and 1 depending on the result of the toss of the coin. Okay. So encryption of MB will be returned to the adversary. Let's call it CB, the ciphertext. Okay. Now adversary has to say CB is an encryption of M0 or M1. Okay. That is the concept of perfect indistinguishability, that if the adversary is able to guess the bit B with probability more than half. Okay. So half is already there because adversary can always randomly guess the bit B and say either answer 0 or answer 1, and with probability half it can be correct. But if probability of its being correct is greater than half, then it is not perfectly indistinguishable. So then we will say that adversary has some advantage over half to say whether it is seeing that it is seeing the ciphertext and saying that whether it is encryption of M0 or encryption of M1. That is the game of perfect indistinguishability. Now, in this game, can you think of an attack where adversary can choose M0 and M1 in such way that seeing the encryption of one of them, it can easily say whether it is seeing an encryption of one of those two messages. So you have to think of some attack. I am saying that this is not perfectly indistinguishable, but suggest me two message string M0 and M1 such that if you encrypt them in this way, then you being an adversary, you can determine that which one has been encrypted by the challenger. Okay, I maybe I can discuss the answer. So you being an adversary, what you can do is that you choose M0 and M1 in this way. So your M0 is all L plus 1 bit being 0, and your M1 is first L bit 0 and the last bit is 1. So you just form your M0 and M1 in this way. And what happens is that your key has this form, right? You uniformly sample K1, K2 to KL, and the last K plus L, KL plus 1 bit is XOR of all this. So when your M0 gets encrypted with such a key, so first L bit of the message, so your if M0 is chosen, so because M0 is all 0, this gets XORed with such a key. So you are left with the key itself because you are XORing with all 0. So M0 XOR K gives you C0. Or in other words, what ciphertext you see is exactly equal to the key K. Otherwise, what ciphertext you see is actually negative of, so your last bit, first see, for M1, the first L bits are all 0. So you encrypt it with key K, and your first L bit is the first L bit of the key itself, right? And the last bit is negation of all 0 because last bit is 1. So you negate this value. KL plus 1 was this, and XORed with 1 last bit of the message gives you this. Okay, negation of this bit. So if you see that the ciphertext you receive, if you see that this property is satisfied, that is the parity bit of first L bits of your key is the inverse of your L plus 1 bit of your ciphertext, then you say that, well, the ciphertext I received is actually encryption of M1. Otherwise, you say it is encryption of M0. And that is how, with greater than probability half, you can say that which message was encrypted. So it is not random guess. It is better than random guess. So this key is not perfectly indistinguishable. How many problems in this lecture? Okay, let's see. We have 2 hours for this tutorial session, right? So why are you asking this? How many problems? This is not any defined thing. Okay, so I can I will just roughly keep some questions to cover on in this 2 hours thing. I don't remember actually how many questions are there in this slide. I think this answer is clear. Okay, if you have any doubt, you can ask. You can unmute yourself and ask. I am saying this again and again that let this session be interactive. That way, I would also like to take the session. We can't unmute. Is it the case? Let me check.
No, we are able to unmute.
Mute. Okay, someone can unmute themselves, right?
Yes, yes.
Yes. So, okay. Oh, sorry. So this answer is clear, right, ma'am? I have a doubt from this week's assignment. No, actually, we have been instructed not to discuss particularly some weeks' assignment questions because your submission deadline is not yet over, right? Because there are people who will be taking exam and the assignment scores are also calculated. So your assignments is up to you to solve. And once you submit them, once the submission deadline is over, then in the next week we can discuss them to clear your doubts and all. But right now we can't discuss, okay? So, okay, I think I can proceed with the next question. So this is a question on negligible function. Prove that Pn multiplied with delta n is a negligible function where Pn is a positive polynomial and delta n is a negligible function. You can give some hint to solve it because the question was not explained in the lecture. Okay. Okay, maybe you can ask or let what is a negligible function? Okay, I can discuss that. Negligible function, okay. Okay, I think there is a question about the previous question from Shreyas. If the M0 is chosen as all zeros, then the adversary is free to choose M1 as any message, right? See, if your M0 is chosen all zeros, okay, then I can't unmute. There is a issue from my side. Okay. Okay, I am trying to answer your question, but I would request someone's just some Namita to do your something is happening in my screen. I don't know if everyone is seeing this random sketch coming over screen or not. Please don't do that or remove that. Yeah. Okay. Yes. So coming to Shreyas questions. So M0 is chosen all zeros, and uh, for that your ciphertext is exactly equal to your K. That is clear. But if you are free to choose M1 as any message, then how do you distinguish whether the ciphertext CB you are seeing is encryption of M0 or M1? You are being able to do that with probability greater than half because in case of M1 being chosen in this way, that L number of zeros and last bit 1, because of this way you are choosing M1, what happens is that this condition you can check. So basically for the M1 case, actually you can check your ciphertext has a particular form, that is your last bit of the ciphertext is negation of the parity bit of your first L bit ciphertext. Okay, this property holds because M1 has this probability. Okay, am I clear? Rather, maybe you can choose M0 to be any message for this particular answer I am saying, because M1 being 0 to the power L being 1 gives you this probability of your ciphertext. You are free to choose M0 to be anything maybe. Okay. And if this property satisfies in your ciphertext, then you can answer bit B to be 1. Otherwise, you answer bit B to be 0. Okay. Okay, I am clear now. I feel most of the students cannot unmute by themselves. Might be possible you have disabled the audio. But I don't know if I would have done anything. I am the host of this meeting, then nobody would have been able to unmute themselves, I think. Right? Because I have not done anything in my from my side, okay? Because it is just that the upon entry you will be muted, but I have not done anything that you can't unmute yourself, because some people are able to unmute. You can check on your Zoom meeting side. Okay. Uh, any more questions there? Okay, there is a long message. Acha, this is the assignment question. I think assume you were given a 500 character encrypted message encrypted in Virginia crypto system, in which you know the plaintext word cryptography occurs exactly 2 times, and we know that the ciphertext sequence is the encryption of cryptography. This sequence, okay. The first occurrence starts at character position 24. Second at this position. What is the length of the key used for that? Okay, do you know what Vigenère cipher is? That is my first question to Anu. This is your assignment question. I am not supposed to discuss the question exactly. Yes. So I would suggest to, so the way Vigenère cipher does the encryption is there is some particular key length, like period we say probably. So you map that particular sequence of character with the fixed key, right? So the length of the key is what is asked in your answer. Okay, my meeting will be ending again in 10 minutes, this Zoom link. So please join in the same link again. I am repeating this. Anyway, so okay, at character position 24, the first occurrence start for cryptography, and character position 198. Okay. So maybe you can just calculate the gap and something I think what you can do, I would suggest is that you just do some calculation by hand, take some examples. So maybe you are following some textbook, right? So the textbook we follow for this course is the Kurtz-Lindell Introduction to Modern Cryptography, Jonathan Kurtz and Yehuda Lindell. So you go through that textbook for this Vigenère cipher thing, okay? And there is some example I think worked out in the book, okay? You have to check for the how much difference is there in this where the string starts in the whole text, and what is the key length. There is some relation. If you work out some example by your hand, you will get to see clearly what is happening. Okay. Anu, you just do this. So better than even if I explain na. So it will be hard for me to show the thing what is happening. Next week I will surely discuss this thing. Okay, clearly. But okay, someone has already answered. I was not trying to. Okay, anyway. Officially, I am not instructed to discuss the question, but it's okay. Although the answer is given by Vikas, I think, but still I would suggest that do this example by your hand. You can clearly see what is happening with engineer cipher, how the mapping is going on. Okay, that would be my suggestion. Please do it on by your own at home with some small example. Okay, let me proceed to the next question. So, what is negligible function? Someone asked. So, negligible function is in very broad sense, it is always smaller than inverse of some positive polynomial function. Okay. To explain with, so let's say I am saying that some function delta n is negligible. What do we mean by that is that there will be some positive integer or natural number capital N such that for all values small n greater than capital N, so delta n always takes as input some natural number. Okay, n is always some natural number and it gets mapped to some real value. Okay, real valued function delta n. Now, for all capital, for all small n greater than this particular fixed value of capital N, this value of delta n will always be lesser than inverse of some positive polynomial function. So let's say Pn is a positive polynomial, then there must exist for, so this will satisfy for all positive polynomial. You take any positive polynomial, you will find some capital N such that for all value greater than capital N, delta n will be upper bounded by 1 by P of n. So that is the property that negligible function satisfies. In other words, if you draw the graph of delta n and Pn, a positive polynomial Pn and delta n is negligible function, you will find some junction or some cross point of the two graphs at value capital N, after which the value of delta n is always smaller than, rather I should say, the plot of 1 by Pn and the plot of delta n. There will be a cross point at capital N, and after that cross point, your graph of delta n will have always lesser value than 1 by Pn. So negligible function is basically for very, very large value, its value is negligible, very small, as the name suggests. So that is what negligible function is. Ma'am, what is the name of the book we have to follow? Okay, I am just writing his message. So I think in the NPTEL lecture series by Professor Ashish Choudhury, he has already mentioned in his introduction lecture the name of the book. Introduction to I forgot, something like that. Introduction to Modern Cryptography by Kurtz Lindell. These are two authors, Jonathan Kurtz. Okay. So coming to this particular question, we have to prove that if delta n is negligible, then multiplying delta n with some positive polynomial Pn again gives us another negligible function. So Pn can be any positive polynomial, but Pn multiplied with a negligible function makes the whole function negligible. That is what we need to prove. Yes, it is a negligible function. That is given in the question. You have to prove this. So how do you prove? As I said, so what is the property of negligible function? Delta n is a negligible function. Hence, for every positive polynomial Fn, there exists an n0, which is a natural number, such that for all n greater than n0, this value of delta n is less than 1 by Fn. This is the property of negligible function. Now, if you multiply both sides with positive polynomial Pn, we get Pn into delta n lesser than Pn by delta n, just multiplying both sides with Pn. Now you can see that Fn is a positive polynomial and Pn is also a positive polynomial. So together you can write this as f dash n, another positive polynomial. Ignore this dash. Oh, sorry, this is common. Sorry. So, okay. F dash n is another positive polynomial. You can write, right? F dash n is nothing but Fn by Pn. So, this is another positive polynomial. So, basically, you can say that for all n greater than n0, this Pn into delta n value is always lesser than 1 by f dash n. So, the property of negligible function is satisfied here. So, we conclude that this thing is again a negligible function. Okay. I hope this is clear. So, what is the significance of negligible function? So, in this week, you already have covered the lectures on computational secrecy, I hope, because you are already covering pseudo-random generator. Till pseudo-random generator was the first week's content, I think. So, negligible function has already come up, I think. This is required because let me just brief it. As we saw in the perfect secrecy world, I said that adversary is not allowed to gain absolutely any information rather than the prior information on the message space, right? But in real world, you compromise little bit. What happens is that adversary is allowed to gain negligible amount of advantage than what happened in perfect secrecy case. So you can think of this in a way that in real world, no adversary is unbounded. Adversary does not have unbounded resource. It has bounded resources, limited number of limited amount of memory, limited amount of computational power. It is not allowed to run some algorithm to break an encryption scheme for 500 years, right? Practically. So if you have to break some crypto system, you should take reasonable amount of time and you should do it efficiently, right? So we say them probabilistic polynomial time adversary. If you are acquainted with complexity theory little bit, so you know what is polynomial time, right? So probabilistic polynomial time adversary means the adversary is allowed to run only in polynomial time. Okay, that makes it efficient. Okay, in reasonable time, you have to break the system. Otherwise, no one is allowed to try. So, we were talking about this negligible function example, right? Uh, so, uh, so this question is clear about proving the negligible function. Just confirm me once, then I will proceed to the next question. Okay, Aryan, thank you. So, okay. Next is identify the incorrect statements from the following. A scheme is COA secure if and only if it is KPA secure. So, COA is ciphertext only attack and KPA is known plaintext attack. And second option is a scheme is KPA secure if and only if it is CPA secure. CPA is chosen plaintext attack. And a scheme is CPA secure if and only if it is CCA secure, that is chosen ciphertext attack. So, four names are there. A, B, C. This is Aryan's answer. I will wait for more answer actually. There are four types of security that we were talking about. Achha, okay, by the way, sorry, probably before ending this map, this previous Zoom meeting session, Someone asked about significance of negligible function. Are you there? I forgot who asked. I was talking about that and suddenly the meeting got ended. So maybe I should complete discussing that. Are you there in the meeting? Have you joined back? Who asked about the significance of negligible function? Uh, okay, probably I will just brief it once. So what I am saying is that in perfect secrecy world, the adversary is allowed to know absolutely nothing more than he already knows about the plain text space or plain text distribution. But in real world, that we call it computational world. So in computational secrecy model, we allow some negligible amount of advantage to the adversary, that with that negligible advantage it is allowed to know, or it is allowed to know negligibly more information than it would have known in the perfect world. Okay, so and why that compromise occurs? Because in real world no adversary has unbounded resource means it can be memory, it can be computational power, how powerful CPU you have. So all these things, nothing is unbounded in real world. So in real world we call an adversary as probabilistic polynomial time adversary. Probabilistic means whatever algorithm it runs to while trying to break a crypto system, that algorithm can use randomness in it. So that's why it is probabilistic. It can just toss some coin and depending on the result, it can take some particular path like that. So there are randomness involved inside the algorithm that adversary runs. So we call that adversary probabilistic adversary, and it is polynomial because it is given some limited computational power. Within reasonable time, it has to attack. And so in case of PPT adversary, we allow the adversary to have some negligible advantage than it would have in the perfect secret world. So that's where negligible function comes to the scenario. We will see about how it is being used while we will be discussing some real world encryption scheme, be it or real world cryptographic primitive like pseudo random function, pseudo random generator and all. So we will come to that. Now coming to the current question that we are discussing. So there are four types of security of encryption scheme that are being talked about in this question. First is ciphertext only attack. Second is known plain text attack. Third is chosen plain text attack. And fourth is chosen ciphertext attack. So what happens in all these four cases is that, so any more answer? Someone said ABC all. Incorrect statement. So the answer is actually true. Like your answer was correct. Whoever answered, Aryan. So all these three statements are actually incorrect. Okay, because this if and only if thing is false. So basically, COA security implies a lesser secure model, and we give more security while implementing a KPA secure encryption scheme, even more security while implementing a chosen plaintext secure encryption scheme, and then comes chosen ciphertext. Why? Because in ciphertext only attack, the adversary is allowed to only eavesdrop, or it is looking into the channel where the ciphertext is passing through between sender and receiver. It can just observe some ciphertext. Okay, observing the ciphertext, it has to determine some information about the underlying message. In case of non-plain text attack, the adversary gets access to some table you can think of, where in the table there are some pairs of plain text and ciphertext available. In case of COA security, it does not know the plain text, like it does not know any plain text ciphertext pair beforehand. It suddenly gets to see just the ciphertext. Okay, and it has to guess the information underlying in that particular ciphertext. In KPA attack, the adversary has been provided with some prior information where it has access to mapping to some plaintext ciphertext pair, and utilizing that information table, it will see some other ciphertext which is not present in the table. Of course, it will get to see some other ciphertext, and it tries to utilize the prior information table, the prior information that is available to it in form of plaintext to ciphertext mapping, and then it tries to guess the ciphertext now it has been given to, that what is the underlying message of this. So of course here the adversary is even given more power, right? In the case of KPA security, known plaintext, it is known plaintext because it has been access to some plaintext ciphertext pair. Now in case of CPA security, which is chosen plaintext, there also the adversary has been given access to a table of plaintext ciphertext, but the plaintext entry in that table that the adversary can choose itself. So somehow the adversary is able to make use of some encryption oracle, we say. Oracle is something abstract. You give a query to oracle and you get back some response. That is what we call oracle. Now in encryption oracle simulates the idea that somehow the adversary can give some plaintext to the oracle and its corresponding ciphertext it can see. Okay, so the table it forms as prior information in case of CPA security. So the plaintext entry of the table, choosing them is in the hand of adversary, which is not the case of KPA security. In KPA security also the adversary is provided a table, but the plaintext entry of that table is not in adversary's hand. It is random, so it just get to see some information. Okay, Aryan has some question. I will come to your question. Okay, I will answer that. So in CPA security, the adversary has the power to choose the plaintext entry. Okay, now in the CCA security, the adversary has access to decryption oracle apart from encryption oracle. So in CCA security, the adversary has access to both encryption and decryption oracle. So adversary can choose a plaintext and get to see its corresponding ciphertext, or it can choose some ciphertext from the ciphertext space and it will get to see its corresponding underlying plaintext. Now you will see that, oh, okay, if the adversary has decryption oracle access, then what is the issue? Then the ciphertext that it is seeing passing on the channel, it can just decrypt it from the decryption oracle. But wait, that is not of course the case, because decryption oracle just simulates some real world scenario. Of course, finally the ciphertext the adversary is concerned about, whose underlying message it tries to get access to, that corresponding message it cannot decrypt. So that task is still hard for the adversary. So what we say is that even if with some prior information in form of plaintext ciphertext table is available to the adversary, finally the challenge ciphertext that the adversary has to decrypt, still it should be hard for the adversary to decrypt or to know any information about the underlying message. So the final ciphertext that we call challenge ciphertext is still hard to decrypt, or should be hard to decrypt for a secure encryption scheme to an adversary. Okay. So hope I am clear. So basically, now coming to Aryan's question, that whether they are completely independent. So as I said, that COA security is a lesser secure model than KPA. Then KPA is lesser secure than CPA, and CPA is lesser secure than CCA. Now, if a scheme is CCA secure, then by default it implies CPA security, KPA security, and COA security. So if you achieve CCA security, then you are done. You don't have to worry about the lesser secure model. Okay. But if you have a KPA secure encryption scheme, it may not be CPA secure. But you have CPA secure encryption scheme, it is of course KPA secure. So this is a clear hierarchy. Okay. The most secure scheme is CCA secure. That is the final thing you would want to achieve. Okay. Aryan, is this answer clear? Okay, thank you.
Ma'am, can you hear me?
Yes.
Yes, ma'am. Aryan speaking.
Okay.
Regarding the question, you said COA is the less secure version, and CCA is the
Huh.
secure model
Correct. Correct.
in the terms of difficulty of the security.
Correct.
Okay, so ma'am, I like in this question, if there is one more option, like a scheme is COA secure if and only if it is CCA secure.
No, the if and only if direction what makes it wrong. You can say scheme is COA secure if it is CCA secure. Then it is correct statement. But if and only if means to say the both direction it is correct, right? That COA security implies CCA security and CCA security implies COA security, which is not true. It is true in one direction. That if it is CCA secure, it is COA secure. But if it is COA secure, does not mean that it is CCA secure.
Okay, so like if I add one more option, like a scheme is COA secure, if it is KPA secure, then that statement would be correct or incorrect?
Yes, that should be correct. That should be correct.
Okay, so here the only basically the keyword here aligned which makes the option incorrect is only if it is.
Correct. Whenever you say something if and only if, that implies it should be true in both direction, which is not the case here.
Okay, so if there can be a case where it is COA secure,
Mhm.
but it is not KPA secure.
That can be the case.
Okay, okay, thank you, ma'am. That was
Mm.
my question. Thank you, ma'am, answering.
Okay, so so let's proceed to the next question. Now we enter into the domain of PRG, pseudo random generator. So let G be a secure PRG, then which of the following is not a secure PRG? So, given a secure PRG, you have been provided with some other construction of PRG, possible construction. You have to say whether they are secure or not. So, let me just recapitulate that what a PRG is, pseudo random generator. That is, so basically in real world, generating random number is a computation heavy task. Okay, this is not very trivial. So what we aim for is and nothing is actually like truly randomness is very difficult to achieve. So natural things, natural phenomena, that can be example of true randomness. But whenever you try to do something manually, that is never perfectly random. What at max you can try to achieve is the pseudo randomness. And pseudo random generator is something you use to generate long bit string which looks like random. So what the adversary's task is that it is provided a bit string. It has to distinguish whether it is seeing output of some pseudo random generator or output of some truly random generator. If the adversary is able to do that with more than negligible probability, then we say that it is not a secure PRG. Okay, so this is where the negligible function comes to picture. If I would have been saying that the adversary is able to distinguish the pseudo-random generated string from the truly random generated string with exactly zero probability, then that would have been the truly random generated string, right? That would be perfectly random. If I would have said that the adversary is able to generate a bit string which is indistinguishable from truly random generated string with one probability, or in other words, the adversary is able to distinguish the adversary is unable to distinguish them with probability 0. So that would have been implied that that string is truly random indeed. Okay. But what I am saying that in real world, it is difficult to achieve truly randomness. So we compromise and we are happy with pseudo random string. And then we say that adversary is able to distinguish them with negligible probability. That much probability we admit that, okay, there can be a very small probability with which it is able to distinguish them, but usually it is not able to distinguish. Okay, so with that much probability we are okay to deal with. So that is what negligible function comes to picture. Now, in case of pseudorandom, so let's coming back to this particular question. So there are given 4 options. First is G1S is constructed as GS concatenated with S. So let's proceed with one after another. First, let me check your answer for the first probable construction of PRG. Is it secure or not? What do you think? G is secure, but if you output okay. So let me just mention that the output of PRG has to be greater than the length of the output of PRG should be greater than the length of its input. So the input to a PRG, we call it a seed. S is seed to the PRG, that is some smaller length bit string, and it has to output a greater length bit string. So if the seed has bit length n and output of PRG has length L of n, where L is some function of n, then ln has to be absolutely greater than the length of S. Okay, that is required criteria of pseudo-random generator. Why? Because otherwise there is no purpose of doing a PRG, right? What I said is that generating random number is a difficult task. So the seed is truly random string. So you have some truly random bit string and you want to generate pseudo-random bit string from that small truly random bit string. So that's why length increasing is important. Okay, so that I just wanted to mention. Now tell me, what do you think that if G1S equal to GS concatenated with S is a secure PRG or not? Can you check, like, if this PRG is outputting this string, then seeing this string, can we distinguish that whether this is output of some PRG or not? The algorithm of PRG is public and deterministic, but what you don't know is the seed. The seed is secret, but other than that, not secure. Correct, Aryan, your answer is correct. Can you explain why?
Like adversary can do is like he can suppose seed has some n number of bits
Hmm.
according
Hmm.
S has some n number of bits assigned to it,
Hmm.
and when it is concatenated with G of S,
Hmm.
when adversary receive this G1 of S,
Hmm.
he basically can extract the last number of assigned bits which are assigned to S seed.
Correct.
He can basically extract it, and he can check whether
True.
the
True.
remaining portion is secure or not. And we already know G is already secure.
Yes, but that right. Your answer is correct. So Pran has also responded. Yes, you are correct. It is not secure because S is revealed in the output. That is very much true. It knows the length of the output and length of the input, right? So as you said, G of S may be a L of n length bit string, and the last n bit actually reveals the seed S. And once your seed is revealed, your PRG is no more a secret. And what it can check is that it can just check whether the last n bit, and the algorithm of G is public. So it can just put S inside G and check whether the first half of this input is equal to G of S or not, because it knows S. So it can just check for equality if the first half is output of GS or not with the last bit as input. So then it can distinguish.
Excuse me, ma'am.
Yes.
Ma'am, suppose if, as Aryan said, suppose the S is of, it's a string of n bits,
Hmm.
a binary string, and
Hmm.
G of S is a PRG, and instead of concatenating it after the GS is produced, instead of concatenating it, suppose if we kind of randomly set all the bits, like all the bits of S in between the PRG of G, then will it be a secure PRG? The resulting PRG, will it be a
In
secure
between,
one, or it will be insecure?
I did not get the point in between. So
In
can you
between, as
just
in, like, ma'am, see, suppose G of S is a PRG scheme where it takes n bits and it will produce L bits. Okay.
hmm,
Uh, so S is of n bits, right? So G of S will produce L bits, and in
okay?
between those L bits, if I place again S somewhere in between randomly, then the resulting PRG will be a secure one, or it will be an insecure.
So you are saying that G of is concatenated with some random n number of bits. Are you saying that you will not?
Not exactly concatenating, ma'am, but I'm kind of
Ma'am, what I think he
placing
is
the
trying to
S.
say is basically,
Hmm?
what I think he is trying to say is basically he is dividing G of S into two parts, not necessarily equal, and inserting S inside it. Can we do that?
G of okay. But
So basically,
I think I got your point. Let's say let me just rephrase your question. Let's say GS has length 3n bit or maybe 2n bits. Okay. Let's say
Yes, ma'am.
GS has GS like G is a length doubling pseudo random generator. So S is of n bits and G of S is of 2n bits. So what you are saying is that you will put the first half of GS first, then somewhere in between you will put S, and then you will put like
Yep.
like that you are saying,
Hmm.
right? So
The other
maybe
part of the
the
GS is
first
then again.
first half of GS come first, then S is there, and then last half of GS. So
Yes, ma'am.
till the point you know where S starts. Okay. Even if you place it in between, if you are making this information public that where S starts, let's say your S is starting from n plus 1th bit, then it can have access to S, right? Even if it is in between, but the point, the information is present in the output string of G1 S. If this is known publicly, then you can recover the information about S. But if you are able to just maybe you put the bits of S anywhere in between, then maybe it's okay, but it is not really safe to comment on that. But uh, what your concern is, like first 10 bits is first half of GS, next 10 bits is S, and last 10 bit is last half of GS, but still you can check that, right? You know the middle n bits are bits of S, you put that to the PRG, you get to see the output, and then check whether the first half of G1S is equal to the first half of G of S, and last part of G1S is equal to the second half of G of S, and you are done. You can do that. But apart from that, any other mechanism you can think of that you will make it oblivious to the adversary, that is again a cryptographical problem. It is not really very safe to answer straightforwardly that, okay, I am done designing a secure PRG. Okay.
Okay,
You
ma'am.
have to specify how exactly you do it, that you have to prove formally that no information leakage is there from seeing the output of PRG. Okay. As far as this particular question is concerned, yes, this is not secure, as you all have correctly answered. Coming to the second question, G2S is given as GS concatenated with GS. So just quick answer from your side. This is again very trivial to see. Still, I would wait for your answer.
not secure, ma'am.
Not secure, right? So you can just see the output and check whether the first half is equal to the second half or not. If it is equal, you can say that, well, with probability, like you can say that it is a output of PRG, right? Okay. So this is also not secure. The third one, GS XORed with GS. I would expect answer from others also. You can write in chat. I think this is very trivial. So what you get basically, you are designing a PRG where you are concatenating the same string with, you are XORing the same string with each other. What do you get actually? Yes, output is 0. Very true. So GS GS XORed with GS gives you all 0 string. So clearly, if you are receiving output of PRG all 0, you would very easily guess that this is output of this particular PRG. Otherwise, if it had been truly random string, you will have received some truly random 0 also. So this is also not secure. The last one, again. G4S,
I'm
what
still
do you
not
think?
sure.
Still not secure. So how do you check? You check the output string. If it is the first bit is 1, you say that this is output of PRG. Again, with the non-negligible probability, you will be okay. There is the games drawn actually in my slide. I think these answers are already clear. There is just some mathematical things I have written. I can just go through it once. So it is intuitively, of course, very clear, but from formal point of view, so this is a game going on, right? Let me just take a look at the fourth answer. So if I see it mathematically, there is a verifier and there is an adversary. Okay, verifier's job is to produce either pseudo random string or truly random string. Okay, so what verifier does, it will toss a coin. So the bit B is either 0 or 1. If bit B is 0, then it decides to output pseudo random string. Pseudo random means your string of G4 bits. The meeting is going to end in 10 minutes again. I hope this time they don't again do the delay thing. Anyway, so if B is 0, it decides to output PRG thing. If B is 1, it decides to output a truly random string. Okay. Now adversary's job is to distinguish between them. Adversary gets to see a string. It does not know what was the underlying bit B that verifier tossed a coin and decided. So adversary's strategy will be that if the first bit of Y is 1, return B dash equal to 0. That is, it answers that you gave me a pseudo random string. Otherwise, return B dash equal to 1. That is declaring that you gave me a truly random string. Now, with what probability adversary wins? So, if you see that if B was indeed 0, that is, B was actually a PRG string, and in a way adversary strategy works, then B dash would be 0 with probability 1. If B is 0, then B dash is 0. Right? Because it will, if it is a PRG string, it will always see the first bit is 1 and it will return 0. So this first part of the probability is 1. The second part of the probability, that is the string was actually a truly random string, and it happened to be the case that the first bit of the string was 1. That occurs with probability 1, right? But the adversary sees the first bit 1 and it answers 0, right? So B equal to 1, but adversary wrongly answers B dash equal to 0. That occurs with probability half. So distinguishing advantage of the adversary is 1 minus half. This is how you represent distinguishing advantage of an adversary. Probability of B being 0, and in that case, with how much probability adversary returns B dash equal to 0 minus B is actually 1, and with what probability, then B dash is 0 returned by you. So that distinguishing advantage is half, and half is clearly not a negligible function. And so we say with non-negligible probability, the adversary is able to distinguish between truly random string and pseudo-random string. And so G4 is not a secure PRG. So this is a formal proof. Okay, this is how you formally prove things secure or not secure. Just for the sake of example, I explain this. Anyway, so let's proceed to the next question. Which of the following is or are true about PRG? So PRG is a deterministic algorithm. This is true. I already said, right, that PRG is deterministic. Of course, then second statement is wrong. PRG is not randomized. It is deterministic. We can construct a PRG which is secure against a computationally unbounded adversary. Do you agree that pseudo-random generator can be secure against computationally unbounded adversary? What is your answer? Yes or no?
No, ma'am.
Sorry?
No, ma'am. It won't be
No.
secure.
Correct. So, as I said, in computational secrecy world, the adversary is never computationally bounded. That is why the concept of negligible function comes to picture. So, PRG, in its name, there is this pseudo-random, right? Not truly random. So, pseudo-random generator is secure against a probabilistic polynomial time adversary, not computationally unbounded adversary. Why? The next statement in this option says a computationally unbounded adversary can always determine the seed of a secure PRG by seeing the output of PRG. That is why the third statement is incorrect. So if you are given an adversary which has unbounded computational power, what it can do is that, let's say your seed is n bit long, then you can exhaustively search over the whole seed space. Okay, so it can go through all the 2 to the power n possible value of seed and check that whether g of s is the output that it is seeing. So with unbounded computational power given with the power of exhaustively search the whole seed space, it is always able to able whether it is seeing a truly random output or pseudo-random output. So then PRG is not secure. So PRG's security is always against bounded adversary, not unbounded adversary. Okay. So next question. Again, you were given a secure PRG G which maps m-bit string to n-bit string. Now there are again some other possible construction of PRGs given. We have to say whether they are secure or not. So I think first and third options are complement to each other and second and fourth option are complement to each other. So any one of them will be correct. Let's proceed with one after another. So G dash S1 concatenated with S2 equal to G of S1 XOR G of S2, whether this is secure or not. You can just think of them and say whether, what do you think? Yes, no. Yes, Pran is answering. Well, it is secure. So I will just go through the. So how do I prove that this is secure? So I would just first say like this is the assumption that I am saying, not assumption, like it is true actually. So I am using this result to prove that the given PRG is secure. So given a secure PRG G, G1 S1 concatenated with S2, if it is defined as G of S1 concatenated with G of S2, that will be a secure PRG. So this is because your the whole S1 concatenated with S2, the whole string is pseudo random. Now you are first using the first half of that seed and outputting G of S1, which is pseudo-random, and you are concatenating the second part as G of S2. S1 and S2 are independent of each other. So overall, this thing will be secured. Okay. Now, using this result that G of S1 concatenated with G of S2 is secure, I will prove that this is also secure. Okay. That G of S1 XORed with G of S2. So how do I prove this? For that, I will first assume that, let's say this is not secure. Okay, this is like contrapositive way of proving. So first I will assume that G of S1 XORed with G of S2 is not secure. And then I show if that is the case, then this is also not secure. Okay. But because we know that this is secure, then I will imply that this is also secure. So let's see the proof. So how the verifier, so basically, as I am saying that I am assuming that G of S1 XORed G of S2 is not secure. So here this distinguisher, let's say, is able to distinguish this output of G dash from truly random string. So such a distinguisher exists, and we will use this distinguisher to distinguish output of G1 from output of truly random generator. So my initial verifier, please join in the same meeting link once this meeting gets ended. Okay. So this verifier is sampling. Again, it is tossing a coin. If B is 0, it is outputting the pseudo-random string. Otherwise, it is outputting a truly random string. And it is passing this G of S1 concatenated with G of S2 or truly random string to an adversary. Now, what adversary does? It XORs the first half of Y with the second half of Y, and we call it Y dash, and passes it to this distinguisher, which we believe that is able to distinguish. So basically, after XORing, so whenever this Y dash is getting communicated to the distinguisher D, we are hoping that it is able to distinguish Y dash whether it is a truly random string or pseudo random string. So if it is able to distinguish correctly, that is, if it says that B dash is B double dash is 0, that means Y dash has been generated in this way, that is G of S1 XORed with G of S2. Then we also send back to this verifier. What we send is that we are sending a bit if this B dash, like we are sending same B dash, right? Whatever B double dash is received by the adversary, the same bit is sent back to the verifier. Now, what happens is that the view of distinguisher D is same as G of S1 XOR of G of S2, right? So now whenever B is 0, that is whenever this is actually a pseudo-random string, then D can be used by this adversary A to distinguish that that this response is actually a pseudo-random generator. Okay. So basically what you can say is that if this would have been true, that G of S1 XOR G of S2 is not secure or is distinguishable from a truly random string, then using this distinguisher D, another adversary we can create who can distinguish G of S1 concatenated of G of S2, this string from a truly random string. So not secure of this G dash implies not security of G1. But we already know that G1 is secure. So we conclude that G dash is also secure. Okay, that is how you prove. I hope I am clear. And the next question was G dash of S1 concatenated with S2 is S1 concatenated with G of S2. So do you like to answer whether this is secure or not? So let me answer actually. So what happens is that this can also be proven secure in the similar manner. What we say is that if there is a distinguisher D who can distinguish the output of S1 concatenated with S1 concatenated with G of S2 from a truly random string, then basically the same distinguisher can be used to distinguish G of S2 from a truly random string. But we already know that G is a secure PRG, so G of S2 cannot be distinguished from a truly random string. So contrapositively, we say that G dash is also secure. Okay. So I think this is very much similar to the previous question in the way we can prove this. There is another problem that G is defined in this way. From a n input space, we are mapping to L1 n bit space. Of course, L1 n should be greater than n. Now, if you construct another generator which has G of S joined with all ones of length L1 n, then does that remain still a secure PRG? So, Ajit, would you like to answer this question? G of S is already secure. You are joining this with all one and constructing another PRG. Do you think G1 remains secure? Okay, let me answer. So basically, yes, it still remains secure because joining a bit string with all ones is nothing but complementing that bit string, right? 0 becomes 1 and 1 becomes 0. So you just complement a pseudo-random string. So complementing a pseudo-random string still holds the pseudo-randomness, right? So that's why G1 remains secure. Now for the second construction, G2S equal to GS concatenated with all ones. So I think this is clearly not secure because in this output of G2, the second half of the output string is always 1. So looking at that, you can easily distinguish output of G2S from output of some truly random generator. So the second one is not secure, but the first one is secure. So okay, I think there is another question left. Let G be a pseudorandom generator with expansion factor L of n greater than 2n. So in each of the following cases, say whether G dash is necessarily a pseudorandom generator. So this is how G dash is constructed. GS concatenated with G of S plus 1. Now, how do we solve it? So basically, we assume that let's say H is a secure PRG. Okay, H maps n bit string to 2n bit string. Now we can construct another PRG G defined in this manner, that G of S is nothing but H of first n minus bit string of the seed of H. Okay, or the S. So S is a n bit string, right? Now we define G of S as putting as input the first n minus 1 bit of this. So because H is secure, so even if you provide n minus length bit string to H, the output remains secure, right? So G is obviously secure. But in this way, when you construct G of S and then you construct G dash such that G of S concatenated with G of S plus 1 is another PRG, then what's happened is that S is a n-bit string and S plus 1 will convert the last bit of S from 0 to 1 or 1 to 0, right? Any integer you add it to 1, then if the initial value of S has last bit as 0, then adding 1 to it will make the last bit 1, or if it is 1, then it will make it 0. So nth bit will change. However, because G of S is defined in this manner, that the only first n minus 1 bit of the string is being used in the PRG, then first half and the second half would result into same bit string, right? So S and S+1 only differs in the last bit. But in the definition of PRG, the last bit is not even getting used. Only first n-1 bit are getting used. So first half and second half basically results in the same string. So because the input seed of these two parts are related to each other, that is the weak point of this construction, and we can utilize that weakness to distinguish the output of G-S from any truly random string. And that's why G-S is not secure. So whenever you are asked to prove something is secure, you have to formally prove this, showing that the advantage of the adversary is negligible. And if you have to disprove something, then you have to provide some counter example. So this is a counter example to argue that for any G-S constructed using this manner, G of S concatenated with J of S+1 is not necessarily secure. So, this is not secure, and that is the last question of my slide. So thank you very much for participating, and I am again sorry for the Zoom thing happened in between. 10 minutes delay was there. I will try to find some solution to it. Or otherwise, what we can do is that whenever we see that Zoom meeting is going to be ended, you can consider it as a 10-minute break. What I observed is that I cannot open the Zoom meeting session before again a 10 minutes gap. So you can consider it as break of 10 minutes and then you can join back rather than waiting for nothing. Okay, I cannot open the meeting actually before 10 minutes. That is the restriction from Zoom. So I will tell next week what we are going to do with that. If we have to wait, or if I can find some alternative way to fix this, I will do. Okay. Can we switch to Meet? You mean Google Meet? I think I preferred Zoom only because of the recording session is very much recording is inbuilt in Zoom. But if I use Google Meet, then I have to take help from some another app for meeting recording and all. And so that's why I preferred Zoom. Previously, this restriction was not there. I had used Zoom previously, but anyway, this thing okay, I will let you know. Okay, whatever happens in next week. So anyway, thank you for joining very much. And so let's meet next week, next Saturday at 6 p.m. Okay. Thank you.